Hello everyone, welcome to Gradeup. Let's continue the course on Theory of Machines and Vibrations. This will be the last lecture on the topic. We will be solving some of the previous year questions on the topic of vibration in the GATE, asked in the GATE examination. Let's begin.
Check out the link below for free GATE course that has more than 200 videos along with this video, followed by doubt sessions, previous paper and more than 250 quiz from Gradeup.
Question number 1, asked in 2015 set 1. It says, considering massless rigid rod and small oscillations, the natural frequency in radian per second of the vibration of the system shown in the figure is. This is a figure. A mass is attached, 1 kg mass attached at a distance of 2r from this hinge point, and there is a spring that is at a distance of r from this hinge point. The spring constant is given as 400 Newton meter and the mass is given as 1 kg. We need to find the natural frequency of this system in radian per second. So how we do it? See, what we do, we just give a small deflection to this spring like this, and this mass comes like this, something like this, and let us say this is x. This we give a small disturbance, that is theta, and this is r. So this x becomes equal to r theta. Okay, x become equal to r theta. The torque that is given by k r theta, because this is the r theta is this distance, k into r theta will be the force, and this will be the r, that is force into r, that will become the torque, the restoring torque. Okay, so the restoring torque will be equal to minus k r theta into r. Okay, this will be k r theta into r, or this can be written as minus k square theta. Okay, like this. Then we know that torque is equal to I alpha. Okay, torque will be equal to I alpha. So I alpha will be equal to minus k r square theta, or I alpha plus k r square theta will be equal to 0. Okay, so alpha plus k r square by I theta will be equal to 0, or alpha can be written as theta double dot plus k r square I theta equal to 0. And we know that comparing it with the general equation, that is theta double dot plus omega n square theta equal to 0. From this we get that omega n, that is the natural frequency, is equal to the root of k r square by I. Okay, but what will be I? The question is I, because k we know, r we know. What will be I? I will be equal to m, because we are considering about this point, so m into 2r square, that will be m into 4r square. So omega n will be equal to k r square upon m 4r square, root r square can get cancelled, k is equal to 400, m is equal to 1, so this will be 400 divided by 4 root. So the answer is option number D. Simple question.
Subscribe to our channel and press the bell icon to never miss any update from Gradeup.
Let's see the next question, asked in 2015 set 2. A single degree freedom spring mass system is subjected to a sinusoidal force of 10 Newton amplitude and frequency omega along the axis of the spring. The stiffness of the spring is 150 Newton meter, damping factor is 0.2, and the undamped natural frequency is 10 omega. Okay, at a steady state the amplitude of vibration is approximately, the amplitude, very simple, the straightforward question, amplitude equal to f naught by s, 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square and whole root, like this. Okay, so in this case f is given as 10 Newton and s is given as 150 Newton per meter. Omega by omega n is equal to 0.1, because this is given as 10. Okay, the undamped natural frequency is undamped is omega n, and this is 10 omega, so this becomes 0.1. So what we are left with, damping factor, the zeta is also given as 0.2. You substitute all these values, f naught, this is f naught, s, omega by omega n, and zeta. So you will get a is equal to something like this, 0.066 meters, and the approximate to this is 0.07. The option B, 0.07. Do not get confused with 0.7. It is not 0.7. it is 0.07. This is the correct answer. Okay. Next question, 2015, set 3. Figure shows a single degree of freedom system. The system consists of a massless rigid bar OP hinged at O and the mass M at end P. The natural frequency of the vibration of this system is. Okay. So how we will do this? We will just equate the moments, that is taking the moments about point O equal to 0. Okay. So mg will be the force acting downwards, and there will be, if there is deflection out here, so that deflection will be acting in the opposite direction to this, because if the spring is stretched, the force will act on the upwards direction. So let us say the position of this rod OM becomes somewhat like this after some time. So this becomes, suppose, XS. Okay, the X due to S. So the force mg into this moment 2A minus XS into K, because the force into Kx will be this, into the distance is A, that is equal to 0, or 2mga is equal to Kxs into A. So this A and A goes off, the XS we get as 2mg by K. Okay, we will use the Rayleigh method or the static mass of deflection method in this case, and in that we need to find out the deflection at the point at which mass is attached. We have found this XS, the deflection at this point. We need to find the delta here. So delta by, using that proportionality rule, that delta by 2A is equal to XS by A, or delta is equal to 2XS, which is equal to 2 into 2mg by K. So this is equal to 4mg by K, and we get omega n equal to under root g by delta. So g by delta is 4mg K. This goes, g goes, this becomes K by, this K remains, K by 4m. This is omega n. So Fn we know, that is equal to omega n by 2 pi. So this is equal to 1 by 2 pi omega n is K by 4m. So the answer is option number A, that is frequency in hertz is equal to 1 by 2 pi K by 4m root. Next question, 2016 set 2. A solid disk of radius A is connected to a spring at a point D above the center of the disk. The other end of the spring is fixed to a vertical wall. The disk is free to roll without slipping on the ground. The mass of the disk is m and the spring constant is K. The polar moment of inertia for the disk about the center J is J equal to ma square by 2. The natural frequency of the system in in radian per second is given by. That means in this question omega has been asked. Okay, so what we will do? This question can be best solved by the energy method. Okay, and in that case we first of all find out how many energies are there. There are 3 energies. The first one is considering the mass, the disk. The disk has 2 energies. One is the kinetic energy of the disk, the translational one, and second one, because it says that it's free to roll, that means there is a free rolling without slipping on the ground. That means it's pure rolling. So pure rolling has rotational kinetic energy also. So the one is translational, one is rotational, and the third one, the spring will get stretched when it will move. So there will be the potential energy also that is stored in the spring, that is given by half Sx square. So we writing all the energies first, that is half I omega square rotational kinetic energy plus half mv square, that is the linear translational energy of the linear kinetic energy or the translational kinetic energy of the mass or the disk m, plus the half Sx square, that is the potential energy that is stored in the spring of spring constant S, or in this case you can write it K because the spring constant is given as K, and x square, where x is the stretched of the spring. Okay, so what we do in this case, first of all we need to change these terms because in the answer you can see that I is not there. Okay, and whatever is not there you have to just change it. First of all, x is also not there. Okay, x and all we need to change. See, if this is a plus d, this distance this whole distance from here to here is a plus d, and if this spring rotates by some angle theta, then this distance will be equal to a plus d theta. So this a plus d theta is nothing but the stretch in the spring that is equal to x. Okay, so first writing these terms like this, I has already been given to you as ma square by 2. So writing these terms, converting this equation, that is half I is ma square by 2, okay, omega square plus half m, v is equal to omega r. Okay, so converting this into also like that, omega into r. But what will be r? What will be the r? R will be equal to a, because in this case the r is equal to a. So m omega square a square, okay, plus half k, x is equal to a plus d theta. So a plus d theta square theta square, like this. Okay, these are all the terms that we have converted, I, v and x. Now dE by dt equal to 0. This is the energy method what we do, because there is no friction, so we can differentiate energy with respect to time and make it equal to 0. So what will happen here? Half this ma square by 2 will remain like this. This will become 2 omega d omega by dt. That means it becomes theta double dot, because d omega by dt is alpha, and that can be written as theta double dot, plus half m a square is like this. Omega again becomes 2 omega, omega square becomes 2 omega d omega by dt, that is again theta double dot, plus half k a plus d square remains like this. This becomes 2 theta d theta by dt, that is theta dot. Simple, d theta by dt is omega, that is theta dot, and this is written equal to 0. Okay, so this half and this 2 gets cancelled, this half and this 2 get cancelled, this half and this 2 get cancelled. That is ma square by 2 omega theta double dot plus ma square omega theta double dot plus k a plus d square theta theta dot equal to 0. Omega omega theta dot, this gets cancelled. We are left with theta double dot common. We get ma square by 2 plus ma square plus k a plus d square theta equal to 0. Okay, theta double dot, now this becomes 3 ma square by 2 plus k a plus d square theta equal to 0. Now the equation has been converted into the generalized equation. Okay, you can compare this equation with simply like this, omega theta double dot plus omega n square theta equal to 0, and when you will simplify this, you will get omega n equal to twice of k a plus d square upon 3 ma square whole root, like this. So the answer is option number C. No, not option C, option A. Sorry, this is not C, because here 3 is also there. Correct answer is option A, that is 2k a plus d square upon 3a ma square. Very simple question, just need to convert these expressions properly, that is the I, the V and the X. The only thing is that I is about the center, this V is also of the center, and this X is at the point at which the spring is attached. The question can be anything. The spring might have been attached at this point also, means at a distance x below the radius. So in this case that x will become a minus d. Okay, just you have to see how the spring is attached. If it is at the center, then d will become 0. If the d becomes 0, so the answer will simply become 2k by 3m. In this case like this, because a square will get cancelled from the numerator and denominator. Okay, very simple question. Just follow the steps properly and you will get this question right. Next question, 2016 set 2. A single degree of freedom mass spring system, viscous damper system with mass m, spring constant k and viscous damping coefficient q is critically damped. The correct relation among m, k and q is, this is very simple. The answer is critically damped means zeta equal to 1. So the answer is simple, this is the general expression. We have done this. 2016 set 3. A static deflection of a spring under gravity when a mass of 1 kg is suspended from it is 1 mm. that means the static deflection, that means the delta is given as 1 mm, or this is also equal to 10 to the power minus 3 meter. Okay, assume the acceleration due to gravity, the g is equal to 10 meter per second square. So the natural frequency of the spring mass system omega, and very simple question, g by delta, simply, that is g is 10, this is 10 to the power minus 3 root over, this will become 10 to the power 4 root over, this will become 10 to the power 2 equal to 100 radian per second. Answer is 100. Very simple question. Next, 2017 set 1, the damping ratio for a viscously damped spring mass system governed by the relationship m d2x by dt square plus c dx by dt plus fx equal to ft is given by. Again, very simple question, damping ratio has been asked, that is zeta has been asked. So zeta is equal to c by cc, and cc is equal to that critical damping coefficient. So the answer is c by 2 root km. Next question, 2017 set 2. A mass m is attached to two identical springs having the spring constant k as shown in the figure. The natural frequency omega of this single degree of freedom system is, see in this case, this is the parallel connection of the springs. So the equivalent k will be equal to k plus k, or also given by 2k, and the omega n is equal to k equivalent by the mass m. So this is equal to 2k by m root over. The 2k by m, the answer is option number A, 2k by m. Very simple. Next, 2017 set 2, the radius of gyration of a compound pendulum about the point of suspension is 100 mm. Okay, the distance between the point of suspension and the center of mass is 250 mm. Considering the acceleration due to gravity as 9.81 meter per second square, the natural frequency in radian per second of the compound pendulum is. Okay, in this case, in case of a simple pendulum, if I draw it, okay, this will be done by the torque method. Given a simple deflection like this, given the angle theta, this is m, force will be acting downwards, mg like this, this is L, this will be L sine theta approximately equal to L theta. Okay, so about this force, if we take, we have given it like this, there will be a restoring torque I theta double dot. So I theta double dot plus mg L theta equal to 0. Okay, or theta double dot plus mg L by I theta equal to 0. Comparing it with the general equation omega n square theta equal to 0, we get that omega n is equal to mg L by I root over. Okay, the mass has been given to you as, mass has not been given, no problem, mg L, mass will be equal to simply mk square. Okay, because the radius of gyration has been given, so I is equal to mk square, m and n goes cancel, g is equal to 9.81, the length has been given to you about the point of suspension, this is the radius of gyration, this is the distance, that is 250 upon, this is in mm, okay, we need to convert it 0.25, and k has been given as 100, so this will be 0.1 square, and the root over of this, so you will get the answer, if you find it out, you will get 15.66 radian per second. This is omega n. Very simple question, just you need to do the simple thing what we did in the, while talking about this, the simple pendulum case, the torsion method, only one part, only one case or one example we have done, and that is only the question that has been asked, and that was the question of 2 marks in 2017. Next question, 2018 set 1, a machine of mass m 200 kg is supported on two mounts, each of stiffness k equal to 10 kilonewton per meter. The machine is subjected to an external force in Newton, like this, 50 equal to this. We know that F is equal to F0 sine omega t or cos omega t can be written. So in this case, F0 equal to 50 and omega equal to 5. Assuming only vertical translatory motion, the magnitude of the dynamic force in Newton transmitted to by from each mount, please note this point, each mount to the ground is correct to 2 decimal places. Okay, in this case we see that m is equal to 200 kg. Okay, there are two mounts, k will be same in both, that is 10 and 10. This is again a parallel connection, so k equivalent equal to 2k, so this will be 2 into, because this is 10 kilonewton. Okay, so this will be 1000, that is 10,000 Newton meter, because this is 10 kilonewton, so this will be 10,000 into 2, that is 20,000 Newton per meter. Okay, so we can find the omega n, the natural frequency, as under root k by m. K is equal to 20,000 divided by 200 root over, the 2 zeros goes from here, this becomes 100, so this is equal to 10. Okay, the omega is this, the omega n is this, so we find the omega by omega n as 5 by 10, which is equal to 0.5. 0.5. F naught has been given. Okay, then K equivalent is also given. So we can find there is no damping, because there is no damping, so that zeta will be equal to 0. Supplying in the equation of transmissibility, that is equal to 1 plus 2 zeta omega by omega n square root over 1 plus 1 minus omega by omega n square, this is square, plus 2 zeta omega by omega n square root. Zeta equal to 0, this term goes 0, this term goes 0, this simply remains like this. So this will be 1 over 1 minus omega by omega n is 0.5, square is 0.25, 0.25, this is square, and this root gets cancelled each other. This becomes 1 upon 0.75, this is equal to 100, this becomes 4 by 3. And the transmissibility is equal to Ft by F0, which is equal to 4 by 3, or Ft, that the force transmitted upon the force generated, is 50. So 50 equal to 4 by 3, or we get the transmitted force is equal to 200 by 3, which is equal to 66.667 Newton. But it is asked from the each mount, and as there are 2 mounts, so we divide this force from the each mount, we will get it at 33.33 Newtons, because it is asking from the each mount the total force. This is the total force that has been transmitted, and from the each mount it is transmitted as 33.33 Newtons. Please, that's why I asked you to focus on this words each mount. Okay, so this is all some of the basic questions that have been asked from the vibrations topic. Very simple questions. What we did on the class, all the questions are almost from there only. Okay, so by this we come to the end on the course on theory of machines and vibrations. We will be coming up with some more lecture series in the very short time. Till then, you stay tuned to Gradeup. Solve as many questions as you can from the books, the test series, the mocks. Join the test series of the Gradeup if you haven't enrolled into yet. And if you have any queries, any doubts, you can ask us on the Gradeup app and on the website. Your feedback is always welcome. See you in the next course. Till then, take care. Thank you and